In today's lesson, we focus on the application of the law of acceleration on rigid bodies acted upon by a constant net force. In our first example, the body of interest is a block of ice being pulled along a straight rough road. The given data are the pulling force capital F equals 150 newtons, the acceleration of 2 meters per second squared, and the mass of the block of ice, which is 85 kilograms. We are required to find the amount of kinetic friction that tends to oppose the motion of the block. As usual, we have our vector free body diagram. We assume and represent the block of ice as a rigid particle. Then we ask ourselves, what external forces must be acting on the particle? Along the horizontal axis, there's the pulling force capital F, and we can infer that it's directed to the right. An opposing force of kinetic friction is directed to the left. There are also forces acting along the vertical axis. An upward force, known as the normal force, exerted by the surface on the block of ice, and an equal but opposite or downward force of gravity or the weight of the block of ice. But since these vertical forces do cancel out each other, the vertical net force is zero, and the block of ice has zero vertical acceleration. For this reason, we do not show these vertical forces in our free body diagram anymore. We are just concerned here with the horizontal forces, the pulling force F, and the kinetic friction Fk. As shown in the diagram, the arrow representing the pulling force is longer compared to that of the kinetic friction, meaning we can predict that the magnitude of the unknown kinetic friction should be less than that of the pulling force F. Why is this so? Because we are told that the object is accelerating, and this acceleration is produced by a net force based on Newton's law of acceleration. The net force and the acceleration have the same direction. We therefore emphasize this equation. F net is equal to capital F minus Fk, which is then equal to mass times acceleration. We substitute the green values, the given values for mass and acceleration, or 85 kilogram times 2 meters per second squared, and we get the net force of 170 newtons. Likewise, from the same equation, F net equals capital F minus Fk, we can isolate Fk and get this working formula for Fk. That is, Fk is equal to the pulling force F minus the net force. And substituting the values for F and the F net, we have Fk equals 150 newtons minus 170 newtons. The computed Fk therefore is negative 20 newtons. Now let us check the computed value for net force using the F net equals F minus Fk formula, and that is the F net is equal to 150 newtons minus negative 20 newtons. This gives us 170 newtons, the same value we got earlier. For the second example, we have a person standing on a weighing scale in an elevator. His true weight is given as 480 newtons with an equivalent mass of 48 kilograms. We get his value of mass by simply dividing the weight W by acceleration due to gravity, or g. And we are also told that the elevator is accelerating at 4 meters per second squared directed downward. It follows that the person's acceleration is also equal to 4 meters per second squared. Since the person is inside the elevator, they constitute as one moving system, and we are required to calculate for the weighing scale reading. We denote this with capital T, or the tension force exerted by the elevator's cable. This capital T also represents the apparent weight of the person. By apparent weight means this weight is not the actual or the true weight, but it is rather the result of having a net force that is not equal to the force of gravity. Our vector diagram shows the two vertical forces acting on the person. An upward force, capital T, and a downward force of gravity, or the weight of the person, W. The force of gravity, W, must be greater than the tension T, since the acceleration is directed downward. It follows that the net force is also downward. That is what the next equation is telling us. F net equals weight W minus tension T, and that is equal to MA. Isolating the tension T, we get T equals W minus MA, or the product of the mass and acceleration, or 480 newtons minus 48 kilograms times 4 meters per second squared. Our computed value for the tension, capital T, is therefore equal to 288 newtons. Notice the value of the tension P is less than the true weight of the person. The person in the situation given in the problem has apparently lost weight. Can you state another condition where the same person may also lose weight or possibly gain weight? Tell me your answers, as well as the following question in this comment section. Thanks a lot for now. Till the next video lesson.